Section: Introduction. In this section, we introduce a new technique called Linear Attention Sequence Parallel, LASP, that aims to improve the efficiency of sequence parallelism on linear transformers. The main motivation behind LASP is to address the challenges posed by the increasing size of large language models, LLMs, and longer sequence lengths, which constrain GPU hardware due to memory limitations. LASP divides long sequences into smaller subsequences and distributes them across multiple GPUs for training. Unlike existing methods, LASP fully utilizes the benefits of linear attention features, enhancing parallelism efficiency and usability. Our approach includes a sophisticated communication mechanism based on point-to-point (P2P) communication for exchanging intermediate states during training on GPUs within a node or across multiple nodes. This design maximizes the use of right product kernel tricks in linear attention. One key advantage of LASP is its independence of attention heads partitioning, allowing it to be applied to models with different numbers or styles of attention heads. This flexibility surpasses existing SP methods in terms of adaptability. Our implementation of LASP incorporates system engineering optimizations like kernel fusion and KV state caching, resulting in significantly improved execution efficiency. Furthermore, we have ensured that LASP is compatible with various distributed data parallel (DDP) training methods, which we refer to as the data sequence hybrid parallelism. Through extensive experiments with different model parameters, cluster sizes, and sequence lengths, we have demonstrated that LASP outperforms existing SP methods, enabling an 8-fold increase in sequence length under the same hardware constraints. In summary, our contributions include a novel SP strategy tailored for linear transformers, system engineering optimizations, and enhanced compatibility with DDP training methods. LASP addresses the challenges of training linear attention-based LLMs on GPU clusters efficiently, even in a casual setting. Section Summary. In this section, we introduce the Linear Attention Sequence Parallel (LASP) technique, designed to efficiently parallelize linear transformers by dividing input sequences into subsequence chunks distributed across multiple GPUs. LASP optimizes communication among GPUs using point-to-point (P2P) communication, maximizing the benefits of linear attention features without relying on attention heads partitioning. By incorporating system engineering optimizations like kernel fusion and KV state caching, LASP significantly enhances execution efficiency and can extend sequence lengths up to 8 times longer under the same hardware constraints, surpassing existing sequence parallelism (SP) methods. Section: Data Distribution. In this section, we focus on how we distribute data in LASP for training long sequences on linear transformers in a distributed setting. To handle long sequences efficiently, we split the input data across GPUs, with each GPU working on a subset of subsequences. This helps reduce the memory usage during training. Communication between GPUs is crucial to share intermediate states. The trained model learns from the entire long sequences. For an input sequence of length n, we represent it in an embedding space as x in math bb r n times d, with a feature dimension of d. In LASP, we divide x into t chunks, where t is the sequence parallel size and must be divisible by the distributed world size w. Each GPU gets assigned segmented data chunks. It's important to note that different groups of GPUs receive different data batches, but within the same group, all data chunks come from the same batch. Let's simplify the forward pass in LASP. We temporarily ignore the norm operator and assume w equals t. In this case, GPU with rank 0 gathers all split subsequences into a batch and distributes them across all GPUs. We introduce symbols kv and kv for the linear attention computation. By setting lambda equals 1, we get the standard linear attention. In the forward pass of linear attention with casual mask, we calculate the output for the STH input. In the sequence parallelism scenario, the query, key, and value for a data chunk x_t on rank I are computed. The output within the TTH chunk is determined. The intra-chunk computation can be parallelized across all ranks. However, the inter-chunk computation considers the impact of previous chunks. To calculate inter-chunk, we rearrange the equation. The computation involves both intra and interparts. The interpart depends on the activation state of the previous chunk, requiring a communication operation between ranks. The final forward output is a combination of both intra and interparts. In the backward pass, the TTH chunk needs the previous activation state to compute gradients. To reduce communication, we store the previous activation state in high bandwidth memory, HBM. The complete expression for the forward pass in LASP with W equals T is detailed in the algorithm. Section Summary. In this section, we describe how LASP handles data distribution by partitioning input data along the sequence dimension in a distributed environment, where each GPU trains a subset of subsequences to reduce memory usage. Communication operations are used between GPUs to share intermediate states, ensuring the final model captures knowledge from the entire long sequences. The input sequence of length n is represented in an embedding space X, in math BB (n) times d, partitioned into T chunks in LASP, with each GPU processing different data batches within the same sequence parallel group. Section: Backward Pass. In this section, we will discuss the backward pass of the LASP algorithm. We start by looking at the inverse procedure and define dkv_t for further analysis. When given do_s, we express dkv_s recursively. In the context of sequence parallelism, we consider q_t, k_t, v_t, o_t, do_t for the TTH subsequence chunk on rank I. Similar to the forward pass, we assume t equals I and t equals w. We begin by calculating dq for the TTH data chunk. The computation of dq_t intra can be done independently and in parallel on all GPUs. On the other hand, dq_t inter involves the interdependence of chunks 1 to T1 on chunk T. To compute the interpart, we transform the equation accordingly. Since kv_t is already computed and cached during the forward pass, no communication is needed to obtain it. This allows for parallel calculation of dq_t inter. Moving on to dk, it can also be calculated in parallel within the TTH chunk. The equation for dk is transformed to separate the intra-chunk and inter-chunk components. To compute dkv for the T1 chunk, an update operation is performed. Similarly, for dv, the intrapart can be calculated separately. The equation for dv is transformed to distinguish between the intra and inter-chunk computations. By combining the intra and interparts, we derive the final results for dq_t, dk_t, and dv_t. The backward pass for LASP with W equals T is detailed in the algorithm provided. When analyzing communication in the LASP algorithm, we note that the forward pass involves communication for the kv activation in each linear attention module layer. The communication volume is influenced by the batch size B and the number of heads H. In practical applications, LASP demonstrates advantages in communication efficiency, especially for long sequence parallelism across large GPU clusters. To optimize system engineering, kernel fusion is implemented to enhance the efficiency of LASP on GPU. Additionally, KV state caching is utilized to store the activation in the GPU's memory, reducing the need for recomputation during the backward pass. Section Summary. In this section, we explore the backward pass of the LASP algorithm by analyzing the inverse procedure. We define dkv_t and examine the calculations for dq, dk, and dv in both intra-chunk and inter-chunk scenarios, highlighting the parallelization opportunities and communication requirements for efficient computation. Additionally, we discuss system engineering optimizations such as kernel fusion and KV state caching to enhance the GPU efficiency and memory usage during the backward pass of LASP. Section: Data Sequence Hybrid Parallelism. In this section, we explore data sequence hybrid parallelism, LASP, a technique that differs from traditional data parallelism by splitting data along the sequence dimension instead of the batch dimension. LASP allows for a smaller sequence parallel size that aligns with the distributed world size, resulting in a hybrid parallelism approach. This method, along with sharded data parallelism techniques like zero-series optimizers and FSDP, aims to reduce GPU memory usage during training large models by distributing model states across all GPUs in the distributed environment. Linear attention models, such as linear transformers, use approximation methods to speed up attention matrix calculations without relying on softmax attention. Memory-efficient attention techniques like flash attention and paged attention optimize memory usage during training by minimizing memory reads, writes, and efficiently utilizing cache memory. Sequence parallelism is commonly used in training long sequences for NLP tasks and has been integrated into frameworks like Megatron LM, DeepSpeed, and Colossal I. We conducted experiments to evaluate LASP on models like Transnormer LLM and Linear Transformer, focusing on its scalability with sequence length, convergence, and speed compared to other sequence parallelism methods. Our experiments were performed on a GPU cluster with 128 A180G GPUs using specific hyperparameters and the Atom optimizer. Different DDP backends were tested for compatibility with LASP, including PyTorch DDP, Legacy DDP, FSDP, and Zero Series. Section Summary. In this section, we introduce LASP, a technique that combines data parallelism with sequence parallelism to split input data along both batch and sequence dimensions, enabling more efficient distributed deep learning training. LASP aligns well with sharded data parallelism methods like zero-series optimizers and FSDP, which focus on reducing memory usage during training by distributing model states across GPUs. By integrating these techniques, training large models with long sequences becomes more feasible, enhancing scalability and memory efficiency in neural network training. Section: Scalability and Speed Comparison. In this section, we present the scalability and speed comparison results of our model. We tested the model's performance in terms of throughput and memory usage by varying the sequence lengths and the number of GPUs. Our experiments show that with the LASP implementation, we were able to scale the sequence length up to 4096K using the FSDP backend and up to 2048K using the DDP backend on a TNL model with 1 billion parameters, running on 128 GPUs. One key finding is that the LASP implementation allows for a linear increase in the maximum sequence length capacity, which means that as we increase the number of GPUs, we can also increase the sequence length proportionally. For example, with 16 GPUs, we can train a sequence length of 512K, while with 64 GPUs, 4 times more, we can train a sequence length of 2048K, 4 times more. This linear scalability ensures a high throughput level even with more GPUs. Moreover, our experiments demonstrate that LASP maintains consistent scalability performance under both the FSDP and DDP backends. We also compared the sequence parallelism of our model against existing methods like DeepSpeed Ulysses and Megatron SP on 64 GPUs. Our results show that LASP outperforms these methods in terms of throughput, especially at longer sequence lengths. Additionally, we evaluated the convergence of our model compared to a linear transformer model on the PILE dataset. Both models, with 0.4 billion parameters, showed consistent loss values during training with LASP. This indicates that LASP does not negatively impact model convergence. Furthermore, we conducted experiments to compare the activation memory reduction capabilities of LASP with another method called activation checkpointing. Our results show that LASP significantly reduces activation memory usage per GPU during training. By combining activation checkpointing with LASP, we were able to achieve impressive maximum sequence lengths on a single node using different backends.